This slide introduced the concept of multi-core programming, which is a way of using multiple computing cores to improve the performance and concurrency of application. A computing core is a part of a processor that can execute instruction independently. A processor can have one or more cores depending on its design. There are two types of systems that use multiple core. The first type is multi-CPU system. These are systems that have more than one processor in the computer. Each processor has its own core and memory. The operating system can assign different tasks to different processors depending on the workload and availability. The second type is multi-core system. These are systems that have single processor with multiple core on the same chip. The core share the same memory and cache but can run different instructions in parallel. The operating system can assign different threads to different cores depending on the workload and availability. Multi-threaded programming is a technique of writing applications that can run multiple threads concurrently. A thread is a sequence of instructions that can be executed by a core. An application can have one or more threads depending on its design. Multi-threaded programming can benefit from multi-core system because it can exploit the parallelism of the cores. To illustrate this point, consider an application that has 4 threads. On a system with a single core, the operating system will interleave executions of threads over time, meaning that only one thread can run at a time. On a system with multi-core, however, the operating system can assign each thread to a different core, meaning that some threads can run in parallel at the same time. This can improve the performance and concurrency of the application. In this slide, we will continue to discuss multi-core programming and the difference between concurrency and parallelism. Concurrency and parallelism are two related but distinct concepts in computer science. Concurrency means that a system can support more than one task by allowing all the tasks to make progress. For example, a single core processor can run multiple threads by switching between them quickly. This gives the illusion of simultaneous execution, but in reality, only one thread is running at a time. Parallelism means that a system can perform more than one task simultaneously. For example, a multi-core processor can run multiple threads on different cores at the same time. This increases the performance and efficiency of the system as more work can be done in less time. Therefore, concurrency is a property of the program or algorithm, while parallelism is a property of the hardware or execution environment. A concurrent program can run in parallel if the hardware supports it, But a parallel program cannot run a single core processor. Concurrency is a necessary condition for parallelism, but not a sufficient one. In this slide, we will look at two types of parallelism that can be used in multi-core programming, which is data parallelism and task parallelism. Data parallelism is a technique that distributes subsets of the same data across multiple cores and perform the same operation of each subset. For example, if we want to compute the sum of an array of numbers, we can divide an array into smaller chunks and assign each chunk to a different core. Each core will compute the sum of its chunk, and then we can combine the partial sums to get the final result. Data parallelism is useful when we have a large amount of data that can be processed independently and uniformly. Task parallelism, on the other hand, is a technique that distributes threads across core and each thread performs a unique operation. For example, if we want to sort an array of numbers, we can use a divide and conquer algorithm that splits the array into smaller subarrays, sort them recursively, and then merge them. We can assign each subarray sorting task to a different threads and run them on different cores. Task parallelism is useful when we have a complex problem that can be decomposed into smaller and independent subproblems. As the number of threads grows, so does the architectural support for trading. CPU have cores as well as a hardware threads. Hardware threads are low-level mechanisms that allow multiple threads to run on a single core without switching contexts. For example, the Oracle Spark T4 processor has 8 cores, and each core can run 8 hardware threads simultaneously. This means that the processor can run 64 threads at the same time, which increases the throughput and utilization of the CPU. In this slide, we will discuss some of the challenges and concepts related to multi-core programming. Multi-core programming is the practice of writing software that can run on multiple cores or processors in a system. One of the challenges of multi-core programming is dividing activities. This means that deciding how to split the work among different cores or processors. For example, if we have a program that performs a complex calculation, we may want to divide it into smaller tasks that can be executed in parallel by different cores or processors. Another challenge is balance. This means ensuring that each core or processor has a fair share of work and does not become idle or overloaded. For example, if we have a program that processes a large amount of data, we may want to distribute the data evenly among different cores or processors so that they can finish their work at roughly at the same time. A third challenge is data splitting. This means deciding how to partition the data that is shared or accessed by different core or processor. For example, if we have a program that performs a search on a database, we may want to split the database into smaller chunks that can be searched independently by different core or processors. A fourth challenge is data dependency. This means that dealing with the situation where the output of one task depends on the input of another task. For example, if we have a program that sorts a list of numbers, we may need to merge the sorted sublist produced by different cores or processor into a final sorted list. A fifth challenge is testing and debugging. This means finding and fixing error in Multicore program. For example, if we have a program that uses shared variables or resources among different cores or processors, we may need to ensure that there are no race conditions or deadlocks that can cause incorrect result or crashes. Multicore programming also involves some important concepts such as parallelism and concurrency. Parallelism implies that a system can perform more than one task simultaneously. For example, if we have a system with 4 cores or processor, it can execute 4 tasks at the same time. Concurrency supports more than one task making progress. For example, if we have a system with 1 core or processor, it can still switch between different tasks and give the illusion of parallelism. This is achieved by using a scheduler that allocates CPU time to each task according to some criteria. There are some of main challenges and concepts of multi-core programming. In the next slide, we will see how threads can help us implement multi-core programming. This slide explains the difference between concurrency and parallelism, which are two common processing techniques used by the operating system. Concurrency means that multiple tasks can be executed in an overlapping time period, but not at the same time. The CPU will switch between different tasks and give each one a time slice. This creates the illusion of parallelism, but actually only one task is running at a given moment. Concurrency is useful for minimizing the idle time of the CPU and increasing the amount of work done at a time. However, concurrency can be complicated to implement and debug, especially when multiple tasks access the same resources. Parallelism means that multiple tasks can be executed simultaneously on different processors or cores. Each task can run independently of each other without waiting or interfering. Parallelism is useful for increasing the throughput and computational speed of the system and taking advantage of multiple CPU. However, parallelisms require more hardware resources and coordination between different processors or cores. The figure on the slide shows an example of concurrency and parallelisms on a single core and a multi-core system. On a single core system, four tasks, which is T1, T2, T3, and T4, are executed concurrently by switching between them on one core. On the multi-core system, two tasks, which is T1 and T3, are executed in parallel on one core, and two other tasks, which is T2 and T4, are executed in parallel on another core. This section is about concurrency. Concurrency means that multiple processes or threads can appear to run at the same time even if there is only one processor. In uniprocessor multiprogramming system, there is only one processor that can execute one instruction at a time. However, the processor can switch between different processes and threads very quickly so that each process or thread gets a share of a processor time. This is called interleaving or time sharing. The operating system manages the scheduling of the processes or threads and allocates them to the processor. When the processor switches between different processes or threads, it creates the illusion of simultaneous execution. This is known as concurrent execution. Concurrent execution can improve the performance and responsiveness of the system as well as enable more efficient use of resources. However, concurrent execution also introduces challenges such as synchronization, communication, and coordination among the processes and threads. It must be noted here that concurrent execution is different from parallel execution. Parallel executions means that multiple processes or threads can run at the same time on multiple processors. Parallel executions require a multi-processor system which has more than one processor that can execute instructions simultaneously. Parallel execution can achieve higher speed up and throughput than concurrent execution, but it also requires more complex hardware and software design. Interleaving is a technique that allows multiple processors or threads to share the CPU time. It is also called time slicing or multitasking. In this slide, we can see an example of interleaving three processes, which are P1, P2, and P3. In this slide, each process has some CPU bursts shown as a solid red bars and some I/O bursts is shown as gaps. The CPU scheduler switches between the processors whenever a CPU burst ends or I/O burst begin. This way, the CPU utilization is maximized and the processors can make progress concurrently. The horizontal axis represents time and the vertical axis represents the processes. The arrows indicate the context switches, which are the overhead of switching from one process to another. The context switch time is assumed to be negligible in this example. Interleaving is one of the benefits of using threads, which are lightweight processors that share the same address space and resources. Threads can be created and switched more efficiently than processors, and they can also communicate more easily. Threads can be used to implement parallelism or concurrency in applications that require multiple tasks to be performed simultaneously. A multiprocessor system is a computer system that has two or more processors that share the same memory and peripherals. This allows the system to execute multiple programs or tasks at the same time or to perform parallel processing on some tasks. Parallel processing means that different parts of a task are executed by different processors at the same time. In this slide, we can see an example of multiprocessor system with two processors. The horizontal axis represents time and the vertical bars represent the execution of process of each processor. In this slide, we can observe that the processors on the two processors exhibit two distinct behavior. Firstly, P1, P2, and P3 overlap and interleave with each other. This means that they are not executed continuously but switch between processors at certain points. Secondly, parallel processing occur when both processors execute different processes at the same time. For example, P1 and P2 are executed in parallel at the beginning. P2 and P3 are executed in parallel at the middle, and P1 and P2 are executed in parallel at the end. Multiprocessor systems have some advantage and disadvantage compared to a single processor system. Some of the advantages are they can increase the throughput of the system, which is the number of processes completed per unit of time. The other advantage is they can improve the reliability of the system because if one processor fails, the other processor can continue working. Another advantage is they can be more economical in the long run because they share resources such as memory and peripherals. Some of the disadvantages are they are more expensive to buy and maintain than single processor system. They require more complex operating system and software to manage the coordination and communication between processors. And the last advantage is they may face challenges such as load balancing, synchronization, and memory consistency. In this course, we will learn about more on how multiprocessor systems work and how to design and program them effectively. This slide explains the different contexts in which concurrency arises or occurs in operating system. The first context is multiple applications. This is when the operating system allows multiple programs to run at the same time by sharing the processor time among them. This is called multiprogramming and it improves the utilization and responsiveness of the system. The second context is the structured application. This is when a single application consists of a set of concurrent processes or threads that works together to perform a task. For example, a web browser may have one process for rendering the web page, another for downloading images, and another for handling user input. The third context is operating system structure. This is when the operating system itself is composed of a set of processes or threads that perform various functions. For example, Solaris and Linux are operating systems that use concurrency to handle system call, device drivers, file system, and network protocols. MS-DOS, on the other hand, does not support concurrency and can only run one program at a time. In this slide, we will discuss some aspect of concurrent processing, which is the interleaving and overlapping executions of processes. Concurrent processing can improve the performance and efficiency of a system, but it also introduces some challenges that we need to address. One of these challenges is how to control the synchronization and coordination of concurrent processes. For example, we need to ensure that processes do not interfere with each other's execution or access to shared resources. We will cover this topic in more details in Chapter 6. Another challenge is how to deal with the sharing of global resources among concurrent processes. Global resources are those that are not local to a process, such as a global variable, shared files or database, or I/O devices. Sharing global resources can cause problems such as inconsistency, corruption, or deadlock. For example, if two processes try to modify the same global variable at the same time, they may override each other's changes and produce incorrect results. Or if two processes request the same I/O device simultaneously, they may block each other and prevent any progress. Therefore, we need to design and implement mechanisms and policies that can manage the sharing of global resources in a safe and efficient way. In this slide, we will look at another example of concurrency. Concurrency can also cause some problems when two or more threads needs access to a shared resource that must be used by only one thread at a time. A shared resource is any data or device that can be accessed by multiple threads, such as a file, a printer, a network connection, and etc. For example, suppose that one thread is writing some data to a file on the disk. If another thread tries to write to the same file at the same time, it may overwrite or corrupt the data that the first thread is writing. This is where this can lead to inconsistent or incorrect result in the file. To prevent this problem, we need to use some mechanism to synchronize the access of multiple threads to share the resources. Synchronization means that we ensure that only one thread can use a shared resource at a time while other threads have to wait until the resource is available. This slide introduces the concept of concurrent programming, which is a type of programming focused on executing independent tasks at the same time. One example of concurrent programming is a concurrent processing system, which is a system where one job uses several processors, which is the multiprocessor, to execute set of instructions in parallel. This requires programming language and computer system support to coordinate the access to share resources and avoid conflicts. Concurrent programming has some advantages over sequential programming, such as improving performance, responsiveness, and scalability of application. However, it also introduces some challenges such as synchronization, communication, and deadlocks issue. There are different models and techniques for concurrent programming, such as shared memory, message passing, functional programming, and actor model. Each model has its own benefit and drawbacks, depending on the problem domain and the system architecture. In this slide, we will see some application of concurrent programming, which is a way of writing programs that can execute multiple tasks at the same time. One example of concurrent programming is to speed up the computation of complex expressions, such as the equation in this slide. The equation of this slide is A equals 3 times B times C plus 4 divided by the quantity of D plus E raised to the power of F minus 3. So, if we have only one processor, we have to perform the computation sequentially, where this means that we have to do one operation at a time and store the intermediate result in temporary variables. As a result, this is why it takes a lot of time and memory. The table on the slide shows how the sequential computations works. We start with the operation inside the parenthesis, which is F minus G, and store the difference in a variable called T1. Then we do the same for D plus E and store the sum in T2. Next, we raise T2 to the power of T1 and store the result back in T1. Then, we divide 4 by T1 and store the quotients in T2. After that, we multiply 3 by B and store the product in T1. Then, we multiply T1 by C and store the result back in T1. Finally, we add T1 and T2 and store the sum in A. As you can see, this process requires 7 steps and 7 temporary variables. However, if we have multiple processors, we can use concurrent programming to divide the expression into smaller sub-expressions and assign them to different processors. In this way, we can perform some operation in parallel, which means at the same time, and reduce the numbers of steps and variables needed. This can make the computation faster and more efficient. So, the next step, we will show how this sequential computation in uniprocessor step by step. In this slide, we will continue to look at how a uniprocessor system can process the same equation that we saw in the previous slide. Recall that the equation A equals 3 times B times C plus 4 divided by the quantity of D plus E raised to the power of F minus G. The table on the slide shows the steps that the uniprocessor system takes to compute the equation. Each steps correspond to one operation that the system can perform. For example, in step 1, the system computes the value of F minus G and store it in a temporary variable T1. In step 2, the system computes the value of D plus E and store it in another temporary variable T2. And so on until the final value of A is obtained in step 7. The main point of this slide is to illustrate that a uniprocessor system can only perform one operation at a time, and that has to follow a sequential order of computation. This means that the system has to wait for each operation to finish before moving on to the next one. This can be inefficient and slow, especially if some operation takes longer than others, or if some operation depend on other operations that have not been completed yet. In this slide, we will see how to use multiple processors to compute the same equation as in previous slide. The equation is A equals 3 times B times C plus 4 divided by the quantity of D plus E raised to the power of F minus G. The table shows the steps involved in concurrent computation using 3 processors. Each processor performs a different operation on the input variables and store the result in a temporary variable. For example, processor 1 calculates 3 times B and store it in T1. Processor 2 calculates D plus E and store it in T2. And processor 3 calculates F minus G and store it in T3. In the next step, each processor uses the temporary variables from the previous step to perform another operation. Processor 1 calculates T1 times C and store it in T4. Processor 2 calculates T3 raised to the power of T3 and store it in T5. In the third step, processor 1 calculates 4 divided by value in T5 and store it in T1. In the final step, processor 1 calculates T4 plus T1 and store it in A. By using concurrent processing, we can reduce the number of steps from 7 to 4, which improve the execution time of the equation. In this slide, we will continue from the previous one and show how to perform concurrent processing on a multiprocessor system. Concurrent processing means that multiple processors can execute different parts of a program at the same time, which can improve the performance and efficiency of the system. We will use the same example of an arithmetic expression, which is A equals 3 times B times C plus 4 divided by the quantity of D plus E raised to the power of F minus G. Here, we will assume that we have 3 processors available and we will assign each processor a different task. We will also use some temporary variables to store intermediate results. The table on the slide shows the step of concurrent processing. Each row represents one step and each column represents one processor. The operation column shows what each processor is doing at each step. In step 1, processor computes T1 equals to 3 times B, which is the first part of the expression. Processor 2 computes T2 equals to D plus E, in which is the denominator of the second part of the expression. Processor 3 computes T3 equals to F minus G, which is the exponent of the export part of the expression. In step 2, processor 1 updates A with T1 times C, which is the result of multiplying T1 by C. Processor 2 computes T5 equals to T2 to the power of T3, in which is the result of raising T2 to the power of T3. For processor 3, here it does not do anything in this step. Okay, so in step 3, processor 1 computes T4 equals to 4 divided by T5, which is the result of dividing 4 by T5. Processor 2 does nothing in this step. Also, the same with processor 3, where it does nothing in this step too. In step 4, processor 1 computes A equals to T4 plus T1, which is the final result of adding T4 and T1. Here, processor 2 does nothing in this step. Also, same, processor 3 does not do anything in this step. At the end of the step 4, processor 1 has computed A and stored it in memory. The other processor have finished their task and are in idle. So basically, this is how concurrent processing works on multiprocessor system, where this will allow us to divide a complex problem into smaller subproblems and assign them to different processors. We can see numbers of threads for each process in Windows 10 or 11 by using Task Manager application. First, open the Task Manager by pressing Ctrl, Shift, and Escape on your keyboard. If the Task Manager starts in its compact view, click or tap on More Details to open the full version of Task Manager. After that, click or tap on the Details tab. Now you can see list of running processes with some detailed information of each process in your Windows 10 and 11. Right-click on one of the items in the title and press on the Select Column option. In the list that opened, scroll down to Threads, mark it, and press OK. Now you can see the number of threads for each process in your Windows operating system. That's all for this video lecture on Chapter 4 of Operating System course related to threads in operating system topic. I hope you can understand what is thread, how threads work in operating system, and the benefit of threads concept in operating system. Additionally, it is essential for you all to grasp the relationship between threads, concurrency, and parallelism concepts in operating system. See you in the next chapter.